present today an important topics, the cavitation of hydraulic machines. Here I have indicated the picture of a Francis turbine where you can appreciate that there are significant damage of blades due to cavitation. The contents of the lecture are cavitation in reaction turbine, critical cavitation parameter, the cavitation in pumps. Here I have presented a figure which is the schematic of a reaction turbine, and the turbine here is connected by the penstock which leads water to the turbine, and then water is being discharged by a drop tube. Thus, drop tube acts as a diffuser connecting the runner exit to the tail race where the water is being finally discharged. Further, one should note that the drop tube being a diffuser, the equivalent divergence angle must be limited by 8 degrees to prevent the flow separations. Purpose of the drop tube are illustrated here in brief. That drop tube allows the runner to install above the tail race without any drop of available head. Moreover, the available head for energy conversion is high because of reduced exhaust kinetic energy because of drop tube, and the resultant is a vacuum pressure would be maintained, which is the below that atmospheric pressure at the exit of the runner. Further, I'd like to add that in hydraulic turbines where the reliability, long life, and efficiency are vital, the effects of cavitation must be considered. If the static pressure of liquid becomes equal to its vapor pressure at the existing temperature, the liquid starts boiling, forming bubbles or pockets of vapor. This phenomena is known as cavitation. The cavitation in hydraulic turbines can occur on the suction surface of the runner or at the inlet to the drop tube where the static pressure is low due to the hydrodynamic action of blades. If cavitation occurs, then pitting of the surfaces, fatigue cracking, and partial collapse of blades, reducing performance, can be observed. The vapor bubble either collapses on the surface, leading to pitting or blade erosions, and often even blocking of flow in severe cavitations can be observed. To avoid cavitations, the minimum pressure of a liquid should always be more than its vapor pressure at the working temperature. In a reaction turbine, the minimum pressure is usually occur at the outlet of the runner or at the inlet to the drop tube. I have indicated here the cavitation damage that's occurred on a Francis blade. One can realize the damage is significant at the outlet of the turbine. Furthermore, I have indicated another picture illustrating the flow visualizations that says that cavitations bubble has formed on the suction surface of a Kaplan turbine. So these two are very illustrating images indicating the cavitation damage and also how the flow would look like on cavitations. After a discussion on cavitation for turbines, an illustration of significant damage caused by cavitation on turbine blades, I'd like to derive now the cavitation parameter, which would be used to decide the safe installation of turbine to avoid cavitation. I have presented here the schematic of a draft tube which is connected at the outlet of a reaction turbine. Section EE indicates the exit of the turbine, and the section C3, where the discharge velocity is C3, indicates the exit of the top tube, where the pressure is equal to the atmospheric pressure. And jet be the elevation where the turbine is installed above the tail race. Thus, applying Bernoulli equation between the outlet of the runner and the final discharge into the tail race, we have P divided by rho g plus C squared by 2g plus Z is equal to PA by rho g plus C3 squared divided by 2g plus HFD, where PA being the atmospheric pressure and HFD is the loss, head loss in the top tube. Considering the velocity at the discharge in to be negligibly small, then I can write PE divided by rho g plus C squared by 2g plus Z is equal to PA by rho g plus HFD. That is the equation number 4. Thus, in the equation 4, that is P by rho g plus C squared divided by G plus Z is equal to PA divided by rho g plus HFD. P and CE represents the static pressure and velocity of liquid at the exit of the runner, while PA and HFD denotes the atmospheric pressure and frictional loss in the draft tube, and Z being the height of the turbine above the tail water surface. Furthermore, please note that for an increased value of CE, the static pressure will decrease, and hence the cavitation is more susceptible to occur. The condition for which the cavitation would not happen if PE is greater than PV, where PV represents the vapor pressure of liquid at the working temperature. For a given machine operating at its design condition, one useful parameter is the critical cavitation parameter sigma c. This is referred to as Thomas cavitation parameter after the German engineer Thomas, N is defined as C squared divided by twice G is equal to sigma C into H, which is the equation number 5. Here, the dynamic head at the exit of the impeller is assumed to be proportional to the available head to the turbine, and sigma C is the proportionality constant, which can be related to the specific speed of the machines. I have presented here a figure illustrating the variation of critical cavitation coefficient sigma C with respect to non-dimensional power specific speed, omega SP, in radian for Francis and Kaplan turbine. Please note that this is the region where there will be no cavitation, so it's a sub-region for values of sigma, and this region is the region where cavitation would occur. So you should not run the pump when the sigma value would fall in this region. Another figure I have presented where I have indicated the vapor pressure of water as a function of temperature. Now in equation 4, replacing C squared over 2G, that is velocity head, by sigma C into H, and neglecting the losses in the duct tube, we have PE divided by rho G plus sigma C into H plus Z is equal to PA divided by rho G. Thus, we have sigma C is equal to PA divided by rho G minus PE by rho G minus Z divided by H. That's equation number 7. Now in this equation, we can consider a limiting case when the cavitation would not occur if P is equal to PV, where PV is the vapor pressure of liquid at the working temperature. Thus, we may define another useful parameter relating to cavitation as sigma is equal to PA by rho G minus PV by rho G minus Z divided by H. That is equation number 8. That means what we have done, PE I have replaced by PV here. Therefore, please note that for cavitation not to occur, sigma must be greater than sigma C. Since PE would be greater than PV. The numerator of equation 8 is an important parameter in the context of cavitation, which is the available suction head at the exit of the turbine and usually referred as the net positive suction head, NPSH, which can be stated as NPSH is equal to PA divided by rho G minus PV by rho G minus Z. That is equation number 9. Please note that either an increase of Z or H would reduce the value of sigma. Further, to determine whether the cavitation is likely to occur in a particular installation, the value of sigma may be calculated. when the value of sigma is greater than the value of sigma c for a particular design of the turbine, the cavitation would not occur. Here, please note that value of sigma is equal to PA by rho g minus PV by rho g minus Z by H, and sigma c is equal to PA by rho g minus PE by rho g minus Z divided by H, where PE is the minimum pressure at the exit of the run. In practice, the value of sigma c is used to determine the maximum elevation of a turbine above the tail water surface for cavitation to be avoided. The parameter sigma increases with an increase in specific speed, as illustrated earlier, and hence the turbine having higher specific speeds must be installed closer to the tail water level. I would like to present now the cavitations for a pump impeller. Please note that the cavitation originates on the suction surface at inlet of a pump impeller, while the cavitations occurs at the exit of a turbine. This is a significant difference between a turbine and a pump impeller with respect to cavitations. I will now concentrate on cavitation in pumps. A pump is a device where the mechanical energy is transferred to the fluid by the hydrodynamic action of a rotating impeller. A pump might be a radial flow, axial flow, or mixed flow constructions depending on the application. We have already discussed in detail the hydrodynamic theory behind a centrifugal or an axial flow machines. Thus here we'll restrict to cavitations occurring in a pump, which is an important topic that needs discussion. Please note that the cavitation here is likely to occur at the inlet to the pump, where the pressure becomes minimum and lower than the atmospheric pressure. Note here that for a turbine, cavitations occurs at the exit of the impeller, while for a pump it would occur at inlet, where the pressure is less than the atmospheric pressure. Please note that for a pump, the bubble originates on the suction surface near the inlet, where the pressure is low, and the travel along the flow and collapse towards the exit of the impeller, where the static pressure increases again. This collapse of the bubble leads to the pitching and thus erosion of the surface, illustrating the significant damage. Thus, a figure is indicated here where one can appreciate that a bubble originates on the suction surface near the inlet of a radial flow impeller, and the collapse towards the end of the impeller, creating a significant erosion of the blade surface and damage. Furthermore, if you take a mixed flow pump, you'll realize Although the bubble is originating on the suction surface near inlet, the significant damage occurs at the exit of the impeller. I have presented here the schematic of a pumping system along with the sump and the reservoir. Please note that the section 1 indicates inlet to the pump, while the section 2 denotes the exit from the pump. Here Z1 and Z2 be the elevation at inlet and exit of the pump from the sump, and H be the difference of elevation between the reservoir and the sump. Thus H is the head developed by the pump. So thus applying Bernoulli equation, the total head at entry and exit of the pump can be stated as H1 is equal to P1 by rho g plus C1 square by 2g plus Z1, where P1 and C1 be the static pressure and velocity at inlet to the pump, and similarly H2 be the P2 by rho g plus C2 square divided by 2g plus Z2. Thus P2 and C2 be the pressure, static pressure, and the velocity at exit of the pump. Therefore, the head developed H can be stated as H2 minus H1, that's equal to P2 by rho g plus C2 square by 2g plus Z2 minus P1 by rho g plus C1 square by 2g minus Z1, which is the equation number 3. Again, applying Bernoulli equation between the liquid surface in the sump and at the entry to the pump, we have P1 divided by rho g plus C1 square by 2g plus Z1 is equal to PA by rho g minus HF, that's equation number 4, where P1 is the minimum pressure P minimum at the entry to the pump. C1 squared by 2g is the velocity head. Z1 is the elevation from the liquid surface in the sump where the pump has been installed, PA being the atmospheric pressure, and HF is the heat loss in the suction pipe. Here, as before, I will define the critical cavitation parameter for a pump and NPSH, that is net positive suction head, as I had already defined for a turbine. Strainers and non-return valves are commonly fitted to the intake pipe. Thus, the term HF must include losses occurring in these devices along with the losses caused by the pipe friction and bends in the pipeline. For a given design of pump operating at a specified condition, the velocity head at suction, that may also be referred as the suction head, can be thought of proportional to the head developed by the pump. Thus, we can write C1 squared by 2G is equal to sigma C into H, where the parameter sigma C is known as the critical cavitation parameter. Thus, in equation 4, replacing the velocity head by sigma C into H, we have P minimum divided by rho G plus sigma C into H plus Z1 is equal to PA divided by rho G minus HF, which yields to sigma C is equal to PA by rho G minus P minimum by rho G minus Z1 minus HF divided by H. That is the equation number 5, which is very important, that gives the value of critical cavitation parameter. Here please note that the loss in the pipeline HF should be as minimum as possible. We know that to avoid cavitation, the minimum pressure at the entry to the pump must be greater than the vapor pressure PV of liquid at the working temperature. We should now define a parameter sigma such that sigma is equal to PA by rho G minus PV by rho G minus Z1 minus HF divided by H, where H is the head developed by the pump. So thus the cavitation parameter sigma is given by equation number 6. Therefore, for cavitation not to occur for a certain installation of pump, sigma must be greater than sigma C. That is, in that case, P minimum occurring at the suction end of a pump must be greater than vapor pressure at the working temperature. Furthermore, the numerator of equation number 6 is referred to as the net positive suction head, NPSH, which is an important parameter in the context of cavitation, as stated earlier, at the inlet of a pump, and is defined as NPSH is equal to PA divided by rho G minus PV by rho G minus Z1 minus HF. Thus, sigma is equal to NPSH by H. In order that sigma should have a large value, Z must be as small as possible. In some installation, the pump is installed even below the liquid level of the sump to avoid cavitation. In those cases where the pump is installed below the liquid level, Z becomes negative. And this kind of pump is called submersible pump. Here I have indicated the cavitation damage in case of pump, and these pictures have already been explained. In this lecture, I have discussed about cavitation of turbines and pump, and also I have defined the critical cavitation parameter that helps us to decide the same level where the turbine or pump to be installed to avoid cavitation. Thank you for listening.